Hi, Year 10s. So what I'm going to be doing is I'm going to be going through the practice test and make a set of solutions for you. I'm actually going to use this as an opportunity to reteach you some of this stuff as well. So if you happen to be away, which a lot of you were during a lot of these lessons, hopefully I can quickly and effectively teach you the actual material itself so that you'll feel comfortable. So first things first, we'll just go straight into it. The first question: which subatomic particle is responsible for the identity of an element? So very simply, it is going to be actually let's choose red. So protons, the proton number is equal to the atomic number, and this bit here is unique to each element. So, for example, carbon has 6 protons, no matter what. Lithium has 3 protons, no matter what. So, even though the number of electrons often goes with that, that doesn't determine the actual identity of the substance. Okay, so the electron configuration of phosphorus. So to work this out, we need to first scroll all the way down to the periodic table, or you'll have this. You should have access to this anyway. We're going to find phosphorus. So scroll all the way down, and we're looking for phosphorus. So as we go along, you should see phosphorus just here, number 15. Now, phosphorus is atomic number 15, which means it has 15 protons. And when it is neutral, so it has no excess charge one way or the other, the number of protons equals the number of electrons. So that means 15 protons and 15 electrons. So let's scroll back up. So here we go. So atomic number for phosphorus is 15. Therefore, there's 15 protons and 15 electrons if it's neutral. And because we haven't, it's not telling us phosphorus is positive or negative, we have to assume that it is neutral. So the number of electrons should equal 15. And that is, the important thing is, that is total. So first of all, option B, we can cancel that out straight away because even though it has 15, the number 15 there, that's in the outer shell, and we need 15 in total. So it's definitely not this one. D has way more than 15 in total, so we can get rid of that as well. And that leaves 285, so that is 15 in total, or 4, 8, and 2. So that is 12, 14. So we already can tell that it's going to be the top one here. But another reason, apart from the total number, that C is wrong is that number there. So this one here is also wrong. You cannot have greater than 2 electrons in first shell. So assuming this was 4, 8, 3, meaning a total of 15, we cannot have that because this first shell is wrong. So remember that we have 2, 8, 18, and then we have 4 times 32. These are the absolute maximums you can fit in each, or even though normally we're going to expect to see something like 2, 8, 8, and then maybe 2 or more. Okay, cool. Moving on. So this next bit says isotopes of an element have different numbers of protons, neutrons, electrons, or charges. Now the important bit here is that an isotope, is same element but different mass. So they weigh at different amounts. So remembering that electrons have very, very low mass, which means they don't contribute significantly to the mass of an element. They have nothing to do with our different mass component. Charges, not really relevant here. Actually, charges are not really relevant here either. But protons here, the important bit here is we're looking for something that has different numbers of protons. If that was the case, it would not be the same element. So that's why this is wrong as well. Can't be protons because if they had different numbers of protons, they would be different elements. So if it's not electrons and not protons, they're the only bits that are charged. It can't be charges. That leaves neutrons. And that is correct. So neutrons are the ones that can change, which will change the mass of the element without changing what type of element it is. Okay, so it says here an atom with the electron configuration of 286 would be expected to form an ionic charge of what? So we have 4 options here. Now, what you need to remember is that elements try, so they don't really try, they're not thinking, but just as a way to remember, elements try to have full outer shells. Now, when I say full here, full can equal 8 or 18 in the third shell. So if we have, so 2, 8 is happy, 2, 8, 8 is also happy, 2, 8, 18 would be happy. In this particular case, because we have 286, we are closest to this one here. So we're going to try to turn 286 into 288. If we tried to turn it into this one here, we would have to lose 6 electrons, which is not easy to do. So if we're trying to get from 286 to 288, this being the same number of electrons here as argon, which has 18 electrons, we need to gain 2. So we need to turn this into 8. Now if we gain 2 electrons, so we gain 2 electrons, our ion will have 2 excess negative charges, which first of all is going to knock out these 2 because these involve either gaining 6 or losing 6. So we're left with the +2 or the -2. Because we're gaining 2 negative charges, we are going to have an overall negative ion. +2 is if you lose 2 electrons. This one here is if we gain 2 electrons. This would be losing 6 electrons, and this would be gaining 6 electrons. So it's going to be B. Okay, moving on. So we have question 5. It says, which element can be found in period 4 and group 2? To do this one, you need to remember that periods are rows and groups are columns. So we're in row 4, column 2. So we're going to scroll down. Remember, row 4, column 2. Let's scroll down on the periodic table. Row 4, so this is 1, 2, 3, 4. And column 2, which is 1, 2, that gives us calcium right here. So scrolling back up, the element we're looking for is going to be calcium. Now, all the other ones are going to be different. If you messed up and thought that it was column 4 and row 2, the other answer, column 4, which is probably you're looking at these ones here, 1, 2, 3, 4, and group 2 would be probably and row 2 would be this row here. That would mean probably carbon if you made that mistake. But you're not going to make that mistake because you've listened to this video. Cool. Now, row 4, column 2 is calcium. Okay, now, question 6. The Lewis dot structure represents the distribution of electrons in the atom's nucleus, the arrangement of protons and neutrons in the atom's nucleus, the distribution of valence electrons around the atomic symbol, or the arrangement of ions in a crystal lattice. So we'll go back and just try and remember what a Lewis dot structure is. It involves the symbol. So let's pick a random element. let's pick lithium, and you need to have the atomic symbol there. Then the next thing you do is you put in the number of electrons in the outer shell. So remember, outer shell is another name for valence, the valence shell. And in this case, with lithium, the outer shell, the number of electrons it has is, because it's in group 1, it has one outer shell electron. It has 1, 2, 3 in total, 2 in the first, 1 in the next shell, which gives us our one outer shell electron. So we would draw this like that. Now, it has nothing to do with electrons in the atom's nucleus because there are no electrons in the atom's nucleus, so it's not that one. The arrangement of protons and neutrons in the atom's nucleus. This does not show us anything about the nucleus at all, so that is wrong. This doesn't tell us about the ions in a crystal lattice at all, so we are going to get rid of that, and it leaves the valence electrons, which is the outer shell, around the atomic symbol, which is correct. So it is going to be C. Okay, so 7. For this video, we'll just go through the, the multiple choice first, and then I'll do the others in a separate video. So it says, which group of elements in the periodic table is known as the noble gases? So we've covered this heaps and heaps and heaps. The noble gases are the only ones that are gases, almost the only ones that are gases, and that is this column here. So the noble gases are elements that are pretty much all gases at room temperature, and they don't really like to react with anything at all. Reason being that they have their happy outer shell, and chemical reactions are elements trying to get their happy outer shells. So in this case, group 18 is our our noble gases. So if we scroll back up, it is group 18. Group 1 are our alkali metals. Group 2 are alkaline earth metals. Group 17 are halogens, and that leaves our noble gases as number 18. So these are the ones you need to remember. Okay, so they're just the names of them, and they're the most common ones that we use, so they're the ones we remember. So number 8, we have, which of the following is an example of an ionic compound? You need to remember this fact here. There's ionic compounds made from metal plus non-metal. So you've got a metal atom and non-metal atoms coming together, and they form ionic compounds. So we can go through this list and work out which ones have metals and non-metals. Metals being, so if we have the periodic table here, something like that, and a whole bunch of stuff there. Then we have our group over there, and even the ones down here. Pretty much everything left of the ones over here, these are all considered metals. Therefore, we're looking for something from this red shaded area and something from the non-metal area. Carbon and oxygen are both here and here, so that is, they are both non-metals. Hydrogen, actually, we should probably be very careful over here because hydrogen, even though it's sitting over on the left-hand side here, it is not considered a metal. The reason it's sitting over there is because it's got one electron in the outer shell, or it's got one electron that's not happy, but it is not an ionic compound. Hydrogen is not a metal. Therefore, oxygen from over here, hydrogen here, is not considered one. So this is a little bit tricky. Similarly, carbons, so if carbon's just there and hydrogen's here, we both know they're both non-metals. So sorry, let's not highlight that one. Carbon and hydrogen are both non-metals as well, so we'll get rid of that. Now, sodium is a metal and a non-metal together.